This video will continue our discussion of parametric equations of a line in space. Here is the theorem written out in nice pretty script. We went over the theory on where these two types of equations come from, parametric and symmetric equations, in the last video. Let's go ahead and do a direction. I have some notes here, but I'm going to go over those notes in the problem. Okay, so it says find the equation of the line containing the point P and the point Q. So I'm going to keep writing this because we're going to have a bunch of things that we're going to be finding. So I'm going to write out what we need to find. So to create a line, we need a point and we need a directional vector. All right, well, we have a point. We can just take our choice. So either one of those will work. I'm just going to go with the first one to keep our lives easy. So I'll write down that. The point will be 5, 3, -3, and -2/5, yeah. Right, to create my directional vector, I can just use the 2 points that are on the line. If I create a vector using those 2 points, that describes the direction of the line. All right, so that is, try to do a better angle bracket there. I got -2/3 minus 5/3. I got 2/3 plus 3. And then I got 1 plus 2/5. That's subtracting each one. So PQ, my directional vector, is, okay, that's -7/3. 3 is 9/3, so this is actually 11/3. And then 1 is 5/5, so this is just 7/5. All right. Now, we can use that. I don't like it because it's nasty with all the 3s and the 5s and stuff. I would like to use something else. The only point the directional vector is literally for a direction. Magnitude does not matter. Meaning, I don't care how long this vector is. All I care about is if it describes the direction of the line. So what I'm going to do is I'm going to take this vector and use it to create a new directional vector. Use directional vector, and then we're going to make this easier on us. So V, sorry for the weird slant there. V is going to be, okay, remember there was from our videos, we talked about that when I multiply a vector by a scalar, it changes the length of my vector, but it doesn't change the direction. So I actually can multiply by anything I want here, and what I'm going to do is do 15. The reason I'm doing 15 is it is the common denominator of everything in my vector. So when I multiply it, things cancel. Let's go below here. So V will be, okay, 15 and 3 cancels a 5. I got -35. 3 and 15 is 5. I get 55. 15 and 5 cancel, leaving a 3, leaving me with 21. So there's my directional vector. It is much prettier because there are no fractions. Okay, so if I write out my parametric, and we're going to do both. Okay, parametric will be x equals x naught. Okay, that's 5/3 minus 35t. Y is going to be -3 plus 55t. Z will be -2/5 plus 21t. So there's one good answer. And then symmetric. Okay, it's going to be x minus 5/3 over minus 35. Sorry, my lines are a little shaky. I'm at the bottom of my iPad. And then y will be y plus 3 over 55. And then the z one will be z plus 2/5 over 21. Those are our symmetric equations. All right, so that's how we do that. Remember, the big point here is this. I need you guys to get that in your head. We need a point and a directional vector. We can manipulate the directional vector by multiplying by a scalar. That's what those notes we're talking about up there. So here's another note just to help you out. Maybe you should try it and then pause, right? And then try it and then unpause. So directional vector should we use if we want our line to move along that? Well, I'm going to, if it were me, I would multiply by the common denominator of 3, 4, and 2, which is 12. So the directional vector that I would use would be 12 times all of this, leaving me with 4, negative 9, and 42. The directional vector is just much prettier. So we can manipulate our directional vector if we're only talking about distance. We should write that. Only can be done if we are talking direction. I'm going to make this smaller so I can fit my whole note. Oops. Fit my whole note in here. Not distance. So if distance is important, we can't change our vector. We can change the vector if we are only talking about direction. So keep that in mind, only direction. Okay, we have another problem here. They gave us two lines, and they want us to show that the two lines are parallel. So what we can grab, and I'm going to grab all the information for this just out of practice. We may not use some of it. Okay, line 1. I can pull a point off that line. 1 point on that line, okay, I'll call that P1, would be from the numbers on top. It's the opposite, so x plus 3, that gets me a negative 3. Y plus 1 gets me a negative 1, and then the last one is 0. We also can grab a directional vector, which is our slope of this line. So numbers on the bottom, 8, 4, negative 8. Okay, let's do the same thing for line 2. All right, point P2. We can grab those, negative 2, 1, 3. And then the directional vector for that are the numbers on the bottom. Okay, well, here's the deal. If we can find a multiple for our vectors, right? Remember, to show two vectors, if we can show the vectors that describe the growth are parallel, then we have shown that the lines are parallel. As long as the vectors are parallel, the lines are parallel, since the vectors describe the growth or the slope of the line. So remember, for parallel vectors, what we're looking for is some c. So we need to find c such that c times v1 equals v2. So let's just plug all that in. So I got c times 8, 4, negative 8, times negative 12, negative 6, 12. I can set up three equations from this. 8c equals negative 12. 4c equals negative 6. And then negative 8c equals 12. And we need all c's to be the same. So c equals, okay, that's going to be what? Negative 3 halves. Here, okay, c is also negative 3 halves. And then the last one, c is negative 3 halves. So, therefore, these three dots mean therefore, v1 is parallel to v2, which implies L1 is parallel to L2. So we have shown that the two lines are parallel by showing that the directional vectors are parallel.